Hello and welcome back to Physics Chapter 8, Light and Optics. This is a short and sweet chapter, though under the surface it requires a lot of wrapping the heads around because there's some tricky questions revolving mirrors and using the lens equation. And I personally dislike this the most in the physics. So I'm not the most comprehensive person to teach it, but I'll try my best. We have familiar equation, where it's just frequency times wavelength equals the speed or the velocity or the speed of light as conventional purposes. We also have Snell's law, which states that the angle of the entering light going in, sine of that will equal to the sine of the angle it exits out of a second medium, depending on the factor n. N is determined by the ratio of the speed of light versus the speed of light within that medium. So for instance, water is kind of more muddled than air, so the speed of light in water is slower than the speed of light in air. So since it's slower, the ratio of n is higher, and as a result, inside water is going to be traveling closer to the what's it called? The normal. And sorry, I just realized I messed this angle up. This angle should be in respect to the normal here. Yes, the normal is a line that divides right in the middle of the medium, perpendicular to the medium. So it enters in and it will curve away from medium into the air because light travels much faster in the air. So you want to speed away from the medium, the normal. And you can get a total internal reflection if you just keep increasing this angle slowly, eventually you just go out straight 90 degrees. And you can find that ratio by n1, the angle, because this sine 2, this angle will be 90 degrees, right, from the medium, so this just cancels out to 1. So you can do n2 over n1 and then inverse sine of that to get the angle of total internal reflection. You can also get the multiple both refraction and reflection, because reflection is just angle equals angle. You get some reflection here, but through different surfaces like oil, for instance, if we have another layer of oil here and another layer of, let's say, water, and you have some light traveling through here, and it's going to have reflection, and it's going to travel through, and it's also going to have another reflection index, right, before I keep going through. Right, so you may have questions with combinations for all of them. And you can just solve them by the angle of subtracting each medium. And you will have the normal for each, and you just need to solve the angle here, 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 in each, and do Snell's law in every way to determine how much the light reflects and refracts. Okay, and mirrors. When we have mirrors, we use this lens equation to go to 1 over f focal length equals 1 over object length and plus 1 over image length. Object length is basically the distance between the object to where the mirror is, and I is where the image length to it is. And f focal length is half of the radius of the circle's curvature. So if we have a concave mirror that goes like this, right, we know every curvature has like a middle, and that radius divided by 2, that's a focal length. And we see that if the image is greater than 0, it is real and in front of the mirror. When we say real, is where light actually hits and goes through it. If the image distance, is less than 0, it's behind the mirror and it's fake, it's illusory, because the light actually doesn't go there. It thinks that it came from there. So if you look in the mirror, well, turns out that you're fake in the mirror. It's not real. And when you do this equation, the magnification, you can do image divided by object distance, and you can get a positive from it. If you get positive from it, the magnification it shows that it is upright, and if you get a negative m, the magnification is upside down. So when you get less than 0, or less than 1 actually, the magnification goes down, it's a demagnification, and when you go up, it's an enlargement of the image, of the object. So we have two types of mirrors, concave and convex. Concave mirror, you have 3 steps. Either you're in front, between the focal length and R and beyond. That creates an image that is real, upside down, as well as larger. When you're right at the focal length, you create no images because it just goes infinity. Right? It goes and converges at infinity. And when you're in front of the focal length in between the mirror, the image is enlarged and appears behind the mirror, and that is virtual and it's upright. For concave, convex mirrors, think about convenience store and the mirrors at the supermarket like TNT. When you're going down, you see those images at the stopway to help with blind spots. They allow you to see a lot wider angle, but everything looks much smaller, right? So that's basically how convex mirrors work. Every image that comes into play appears smaller and behind the mirror, and is virtual. Alright, onto lens. When we have lens basically are mirrors but kind of backwards. If we use a thin lens mirror, then we can just use a mirror's equation. Thin lens basically says that the medium that it uses doesn't matter. Right? It doesn't matter the difference in curvature, but if we use real lens and is basically thick enough, like the curvature here will matter. Right? This curvature is going to be much different, and we have to account for this distance in between the light traveling through the medium. So this is taken into account. N minus 1, which is the speed of the n factor here, and that has to be multiplied by 1 over r, which is the radius of the first curvature minus the radius of the second curvature, to correct for 1 over the focal length. Now, a concave lens is like caved up both sides. It actually diffracts the light like this, so it diverts, and it behaves kind of like a convex lens where it like diverges the light. Whereas convex is like a conversion lens because just like how concave, they concentrate the light to one spot. Now, in concave or divergent lens, or lenses in general, wherever the light goes, remember, if it goes there on the opposite side of the object, then it's real. But if it ends up on the same side of the object, then it's fake because the light actually doesn't end up there. It just appears where the light came from. And you can just work backwards from the lens equation as usual to find out the proper notations and whether it's positive or negative or virtual or upright, so on. And lastly, we have the slits equations. For a single slit experiment, we have A times sine of theta equals n times the wavelength. When you shine the light through a single slit, it's going to make a diffraction pattern, and the first is going to be a maximum of a light fringe, and the next one is going to be a dark fringe or a minima, and basically from a distance from the 0 to the first dark minima, n basically means the number of the dark minima it is, so 1 going up, and a 2, and a 3, so forth. Wavelength is the wavelength of light you're shining through. Sine theta is the angle between here and going into the dark fringe. A is the width of the slit right here. We also have double slit fringe by Young's experiment, and that basically shows that both of these slits, when the lights converge, they behave like particles, and they behave like sine waves, which they can constructive interference and so forth. So light is a wave. Construct interference and create a large white fringe here, and dark fringe, light fringe, dark fringe, light fringe, and so forth. So there are areas of destructive interference where d is the distance between the two fringes, and is n plus half to and times wavelength to find out the position of the dark fringe, basically. All right, and you need to do manipulations involving find out the distance between the 0, the fundamental maxima, to the next dark fringe. All you need to do is just imagine it's far enough distance, d away, that you can just use tan instead of sine. All right, and that's light and optics.